In this demonstration, we are going to take a look at the differences between value and reference types. As you are probably already aware, the int data type is a value type. In other words, when we declare this variable x, it is allocated in something called the stack. The stack is a small data structure that grows like a stack of coins. Every time you add something new to the stack, you're adding like another coin on top of an existing stack of coins. Then when you're done with that particular variable, that is popped off of the stack and pulled off again. And that's how the stack grows and shrinks. Every time you declare a value type within a method like main, this x is now placed on top of the stack of coins, and when it falls out of scope, which is the end curly brace of main, that coin, or x, is then popped off of the stack, making room for something else to be added. And this continues with however many value type variables we add. And just to sum up what the value type variables are that you're most familiar with, we have things like int, we have short, byte, double, float, date time. These are the common value types that you will use on a day-to-day basis. What happens if we try to compare these two variables? We would use if x equals y, and we can put inside curly braces here, console write line, equal. We don't have to do anything too fancy here. And I will stop with a console read line to make sure the program doesn't close on us while we're still reading the screen. And as you can see here, it does output equal. The reason is when you do a comparison like this with two value types, it looks at what the contents are in the stack for those variables, and it compares the two values. So it's basically saying if 10 equals 10, and in fact that is true. What about reference types? I'm going to use a string builder. The reason I'm not going to use a string is because a string is a special type of reference type in that it behaves more like a value type than a reference type. So the equals operator will compare contents, not necessarily memory locations. We'll get to that in just a minute. But let's just create a string builder called SB1. We'll set it equal to new string builder, and we'll pass in ABC. And then we can do another string builder, SB2, and we'll also set that equal to ABC. Now what happens if we try to compare these two variables, SB1 to SB2? I'll just copy what we did above for x and y. They contain the same values, ABC, but watch what happens when we run. And actually, let me put this in as a prefix so we know which ones we're looking at, and we run the code, you'll notice we do not get an entry or an output for ref equals. But why not? They contain the same value. It has to do with how reference types by default compare against each other. The equals operator for all data types does the exact same thing. It compares the contents of the value in the stack at the location for that variable. But remember, reference types don't store their data in the stack. They store their data in another location called the heap. And the stack variable the stack location for that variable contains the address in the heap for that data. So in fact, we have two different stack locations, one for SB1, SB2, but we're also going to have two different heap locations. So SB1 is going to point to one location in the heap. SB2 will point to another location. And when we do this equals, it's basically comparing those two heap locations, and they're not the same, and therefore it will return false. To understand how value type and reference type variables allocate memory in .NET, a visual approach can be very useful. Here we're going to talk about how value type variables allocate their memory. The stack is represented here as a grid, where the first column was going to represent the variable's name, the second column represents an address, and the addresses I'm going to use in this example are completely fictitious. I'm just using them as an example so I don't just put a placeholder or memory location A, memory location B, so you have something a little more visual to understand what's going on here. Size is the third column, which represents how much memory is going to be allocated in the stack for a particular variable. And then finally, the value, which is stored directly in that location in the stack. We'll start by declaring an int called x with the value of 1, 2, 3. As you can see, it is allocated at the bottom of the stack with the value x for the variable name. The address is this arbitrary hexadecimal value, and it's going to take up 4 bytes of memory because it's an int. Notice then the value 1, 2, 3 is stored directly in that location of the stack. You can almost think of the stack like an array. The next variable we declare, y, is going to be a long, and therefore it's going to consume 8 bytes of memory. And notice its address is exactly 4 bytes after y. Also note that the value 456 is placed in the value column for that variable. Next we'll declare another variable of type int called z. So it's going to follow the same basic pattern, except the address now is 10000C. Again, this is hexadecimal, which is explaining why it's C for the last character and why we're not at address 100012. It is also 4 bytes in size, and its value is stored directly there in the value column. What happens when we declare a new int called I and we assign its value to whatever is contained within x? The first part's the same. We just allocate a new 4-byte chunk out of the stack, and that's where I is. But the value this time comes from whatever is in the value column for variable x. So this is a value copy. We copy the value of x into the location for the value of I. Now I and x are completely distinct variables, and if I were to change either I or x, it would be self-contained to that memory location. Therefore, if I became 1, 2, 3, 4, x is still 1, 2, 3. Reference type variables, on the other hand, store their data in 2 different locations. We have the stack, which is going to be almost identical to what we saw with value types, and then we have this memory location called a heap. And the heap is just a big chunk of memory that the CLR will manage, so any reference type data will be stored in that location. If we start with a string builder, which is a reference type variable, it will again be allocated in the stack, just like any other value type variable. So we have the allocation of S1, it's at some arbitrary address, and we give it the size of 4. That is not actually the actual size that's stored in the stack. However, in a 32-bit operating system, we are going to assume that the size corresponds to a location in memory. Because what happens is the value ABC is stored in the heap at some, again, arbitrary location. But watch what happens to the value of S1 in the stack. It receives the address of ABC in the heap. So now you can see how the two are tied together. So the variable S1 is declared in the stack, and it points to that address in the heap where ABC is stored. Creating another string builder, we get the exact same process. Again, another variable is allocated in the stack. Its data is stored in the heap at some arbitrary location that the CLR decides. And then that address from the heap is copied to the value of that particular variable in the stack. This next statement, where we assign S1 to S3, is looking very similar to how we dealt with the value type assignment in the previous demonstration with variables of the value type. However, watch what happens here. We again create another variable in the stack called S3 this time, but the value is copied from the value of S1. Again, it looks just the same as we did in the value type example. So the value is copied directly from the other stack entry. Nothing was copied from the heap in this example. So what this is saying is that both S1 and S3 are pointing to the exact same location in the heap. Therefore, if we make a change to S1 by appending a D to the end of ABC, both S1 and S3 point to the same string, ABCD. So any change made to either S1 or S3 is reflected in the other. That is what happens when you do a reference type variable copy, as I showed here. There are ways around this. If you wish to disconnect S3 from S1, so like value types, they represent two completely different data locations, then you have to do something known as cloning, where you would copy the contents of S1 into a new location in the heap, and then S3 would point to that new location. So now they're completely disconnected. That's for a conversation at a later time, however. So now hopefully it makes more sense why SB1 is not equal to SB2. It's because they both point to different locations in the heap, and that comparison is going to return false. Another feature of reference types is that they default to a value called null, which means it's uninitialized. It's a valid variable. This is not an invalid declaration. SB3 is now allocated in the stack, but what we're assigning to its value is this thing called null, which means it's not pointing to something legal or valid in the heap. It is pointing to the null location, which means it is declared, just not initialized. We can then test SB3 for null at some later point, and then call its constructor as such to initialize it, and now SB3's value in the stack will point to a legal entry in the heap. It's not pointing to null anymore. However, you cannot do this with an int, or any value type for that matter. You'll get an error that says cannot convert null to int because it's a non-nullable value type. You cannot assign null to a value type. You always have to give an int some legal value, like 0. There is a way around this, however. It's called the nullable type. If we wanted to be able to make an int nullable, there are two different ways we can code it. One is to use the longhand syntax, which is nullable with two L's. The type that you're looking for in braces, and we'll call it null z, is equal to new nullable int, and we can pass it the value 12. You'll notice that the nullable int portion of the declaration here is grayed out. And the reason is this is more of the stylistic issue. If you hover over it, it'll say name can be simplified. And what it's really getting at is you can use the C# syntactic sugar to say int question mark null z is equal to 0, or null. So nullable int, or nullable whatever you want to put in here, it's a generic type, so any value type can be placed instead of int within that declaration. That is a wrapper around an int. So essentially it's another data type that either contains a valid int or a Boolean flag indicating it does not have a legal value or null. So it is not a different type of int. It is another data type that encapsulates the int and adds one extra little flag to indicate whether or not it's a legal value or it's uninitialized. In this case, it's uninitialized. And then I can do this traditional test for null, just like I did with the string builder. And then I can assign a legitimate value like so. However, with a nullable int, you have to be careful, because if you ever want to assign its value back to a real int, you cannot just do a direct assignment such as this, because there is the possibility that it contains a null value. Even if we put it within the ifs then block, we still have to do something special to ensure we don't attempt to put a null inside x, because that's just not legal. The easiest way to do this is to use the null coalescing operator, which says if null z is actually null, return this value, -1. Otherwise, it returns the int value from the nullable int. So since it is a legitimate value after this point, it's 0, x will be set equal to 0. If I left this assignment out, now x will be assigned -1. That's what the null coalescing operator does. It checks for the first non-null value from this list of items. Well, there's only 2, so on the left-hand side or the right-hand side, looking at the left-hand side first, if it's a non-null value, that's what comes out of the operator. If it is null, it checks this for nullability. -1 is not null, so then that is a legitimate value and it gets assigned into x. One last thing I want to point out about value and reference types is this concept called boxing. We have already discussed in the past this concept of an object being able to store any value. As you can see from this IntelliSense pop-up, object is a class. All classes are reference types. That being the case, when we stick an integer, which x is, into that, something special has to happen, because all of the data for this object will be stored in the heap. But a value type wants to put its information in the stack. In this particular case, what happens is an entry in the stack for the object is created, and that points to an entry in the heap which holds this value. That is a very inefficient way to store an int, because we have this indirect lookup from the stack to the heap to get the value. This is known as boxing. When you take this int and you're boxing it or wrapping it with this reference type. To read that value back by using like a console write line, for instance, that invokes the read from memory of that int. Again, we have one layer of indirection. It has to check the stack for where obj is stored, and then it pulls the value out of the heap that that entry in the stack points to. Plus, besides performance reasons, there could be functional side effects as well, because when you are dealing with a reference type like this, if I pass that object to another method, that method now has access to the data stored at that location, and it can change it. By default, when you pass an int to a method, it's passed by value. There's nothing that method can do to manipulate it. But if it's passed as an object, that means it's a reference to the data in the heap. Manipulation is now possible. Try not to use the technique of boxing unless you absolutely have to. In the long run, it's going to make for a cleaner and more robust code.